Hi, welcome to this video on enthalpy calculations. So in this video, we're going to focus on how to take a thermochemical equation when we're provided the energy of the reaction that's happening, or the enthalpy of the reaction, and how to use that as a stoichiometry problem to find the total energy that a certain amount of reactant or product would produce. So we're going to use stoichiometry again. So this is an application, an add-on to a stoichiometry unit from before, which we're all really good at now, right? And so we've got our stoichiometry, and then we've got delta H as basically a product or a reactant within the reaction. So it's using it just like you would a normal reactant or a product. You're just using energy instead of the compound itself. So we're treating the energy like the reactant or the product. So an enthalpy calculation is really easy. It's used to find the total energy that's absorbed or released during a chemical reaction. So in the example, let me show you. We've got this thermochemical equation. It says, upon adding solid potassium hydroxide pellets to water, the following reaction takes place. Well, when I add this to water, right, so we're going to do a little plus water right here, what we see happen is it becomes aqueous. Well, really, water is going to split those little ions apart, and so it splits it into potassium ions and hydroxide ions. So the reaction that's taking place here is really overcoming that ionic bond to split those. And so sometimes that requires energy overall, and sometimes it releases energy overall. It just depends on what type of reaction we're talking about. Is it endo or exothermic? Remember, the endo or exothermic part, that's going to be specific to whatever the reaction is that's happening. In this scenario, when I look at this option, right, I see that the energy is plus 43 on the product side. So what does that tell me? Is that tells me this is releasing that much energy. Okay, so when I look at the questions, right, it says, answer the following questions regarding the addition of 14 grams of KOH into the water. So that's my known. That's what it's giving me. So it's telling me I have 14.0 grams of KOH. And what I want to know is, first, is the beaker going to get warmer or colder? Well, if energy is being released, right, the beaker is my surroundings. So overall, it should get warmer. That should be pretty easy, right? Is the reaction endo or exothermic? Well, if my surroundings are getting warmer, then that tells me the reaction released energy, and so that would be exothermic. All right, so question number 3 is where we get into the stoichiometry part. So it says, what is the total heat? So keep in mind, that's my unknown, right? That's what I don't know. And remember, heat is measured in joules. It could be measured in kilojoules, depending on what it asks, right? That is absorbed or released. Well, we already figured out that that was going to be released to complete the dissolution or dissolving of the whole 14 grams of KOH. So this is my known we talked about previously. So we're going to start with our known. I'm going to set that up with 14, one sec. 14, I would help if I actually picked the pencil, 14.0 grams of KOH, right? And so basically here I am. I'm at KOH. For every 1 mole of KOH that I dissolve, right, I'm producing 43 kilojoules. That's really all it is. It's a mole to mole ratio, but now it's mole to energy. But we're still using what's provided. So we want to go grams. Well, if I'm given grams, what's the first thing that we've learned over and over and over and over and over and over and over we do with grams is we convert that to moles. So we would find molar mass. So when I add up the molar mass of KOH, I get 56.11 grams of KOH. Now remember, if it had started me with moles already, I wouldn't need to do this step. So then I have, that goes to 1 mole of KOH, right? Because our mass to mole is always 1. Now here's the only part in enthalpy calculations that's different for stoichiometry. In here, instead of going from reactant to product, my product is now energy, right? So if moles of KOH are down or up, moles of KOH have to go down. And so we look in our reaction, and it's saying in the reaction, for every 1 mole that we use, because that's the coefficient for KOH, we are going to release 43 kilojoules. So keep that in mind. That's how much. So it didn't specifically say if I have to have it in joules or in kilojoules. So I'm going to leave it in kilojoules. Usually with heat, we're dealing with lots of numbers, big numbers, lots of quantity. So we usually put it in kilojoules anyways. So we would go ahead and multiply. So 14 times 43, because they're on top. And it would help if I did that correctly. And then I'm going to divide it by the 56.11 because that's on bottom. And then I want my answer to have 3 significant figures. So it's going to end up being 10.7. And then my units, notice, grams canceled of KOH, moles of KOH canceled. My unit is kilojoules, or energy, which is what I wanted because heat is energy. The only other thing we need to remember to do is we want to make sure that we're including if this energy was absorbed or released. So you would go back and you would make sure that you can either say it's released. So you can go back and put released, or you can put a negative sign. Either or, but somewhere in there has to be an indication that it was released. Okay, let's try one more. So in this practice problem, it's giving me the reaction, and it's saying that I have nitrogen plus 2 oxygens making 2 NO2s. And it's giving me the enthalpy, or the thermochemical equation, with the enthalpy outside of the equation. So it's over here. So what I like to do is I like to put that back into the equation. So I look at what I have. So this is a negative, right? So that means it's exothermic. Hopefully we all caught on to that, right? The negative sign tells me it's exo. So that means the energy is a product. So what I would do is I would write it back in here, right here. So plus, remember it's always positive when we put it into our reaction, and that's going to be plus 33.2 kilojoules. I just like to see it in my reaction. I think it makes it easier to do the stoich. Ignore the fact that I can't write very good when I'm trying to write small. I just like to see it in the reaction when I'm working through it, so that then I can see the stoichiometry a little better. Okay, so the question A says, nitrogen gas is burned with oxygen and nitrogen dioxide is formed. So it's telling me what the reaction is. I want to know how much heat. So again, I want the energy in kilojoules or joules, whatever it is released if 2.33 moles of nitrogen dioxide is produced. So coming back over here to our reaction, right, we look at it and say, okay, well, I have 2.33 moles of this that's being made, right? And so I'm going to start with that. That's going to be my known. So my known is 2.33 moles of NO2. Now we already had this conversation earlier. If I'm already at moles, I don't need molar mass. So then I can just go straight into stoichiometry. So then I'm going to compare. I've got 2 NO2s for every production of 33.2 kilojoules. So down, I will have 2 moles of NO2, right, for the production of 33.2 kilojoules of energy. So that's really all it is. I just made the connection between those two things. So now I know my energy. If I multiply those two, so 2.33 times 33.2 divided by 2. My dog has decided to join my video. Sorry, you can hear the panting. And so my answer is going to be 3 sig figs, which is going to be 38.7 kilojoules. And again, remember produced or released, so I'm going to put a little negative sign there. Don't forget that, because that's always going to be a part of the question. So that's the amount of heat released. In question B, it says if 5.6 moles of N2 is reacted, right, how much energy in joules? So now we throw in a joule here, pay attention to that, is going to be released. Same idea, right? We're going to work through this. So I would go ahead and start with my 5.6 moles of N2, And again, I'm already at moles, so I don't need more mass. Yay. Okay. Remember that N2 is going to be 2 nitrogens. So if you had to find molar mass, you would double it. So a lot of you seem to be missing that a little bit. I'm going to go back up to my equation. For every 1 N2, right here, I am producing 33.2 kilojoules. So down, I will have 1 mole of N2. And up, I'm going to have 33.2 kilojoules. Now the question asked for joules. So we would just do one more thing. What do we know about energy? We know a kilo is always 1,000 of those base units. 1 kilojoule is 1,000 joules. And so when we multiply that, we're going to have a bigger number because obviously we talked about how usually energy is big numbers. And that's why we like it in kilojoules. So in this scenario, I only have 2 sig figs. So my answer I get is actually 1,8, we'll talk about the rounding, 5,920 joules, right? But I want it to be in 2 sig figs, so I want those 2. That's going to round up, so it's going to be 1,9, and then I'm going to put zeros in those other spots. To do that, I need an extra 1, joules. And again, it's negative because we're releasing that energy. You would leave it positive if it was endothermic and the energy was on the other side. All right, so those are some examples. So it's just stoichiometry like we've done and we've practiced a lot, and we're just adding energy in. So now we know how much energy we get from certain quantities of reactants or whatever. If we needed a certain amount of energy, we would know how much of the reactant to burn, right? So we could calculate those theoretically. So it's just the same thing, using it just like it's in the reaction. Before you submit your notes, I want you to try practice problem number 3. Again, remember a lot of times it's easier to add the energy into your equation so that you can see the stoichiometry. And it's going to be very similar to the very first reaction that I did for you. But otherwise, shouldn't be too hard. So try these for yourself, see how you do, and submit that. And if you have any questions, just ask.